All right, silly people, here's the situation. We're going to be calculating the intensity for a diffraction of a light or a sound wave blocked against an object with a straight edge um, using just this equation here and these integrals. The concept isn't actually that important, but the calculus and the um, coding is actually fairly straightforward. Um, so what I'm going to do is, we know that we're going to be plotting stuff and doing square roots and things, so I'm going to go ahead and import numpy as np and also import matplotlib.pyplot as plt, right? And then we have to calculate two integrals for this, and both of them are going to be Gaussian quadrature integrals. So what I'm going to do is I'm going to create two separate user-defined functions for each of the integrands. The first one is, I'm just going to call it the lowercase c of t, which is going to return the cosine of pi times t squared, and then divided by 2, right? And then the other integrand is the same thing pretty much, except it's a sine function instead of a cosine function. So I'll just grab this and put sine here instead, right? Then I'm going to put the calculation of the intensity inside of a function that I'm going to call I of u, right? So, or not even I of u, let's do I of x. That'll be a lot better. So if you just look at these formulas, you do it u is equal to x times the square root of 2 over lambda times z, where lambda and z are variables that we have to define. So I'm going to do lambda equals 1 in accordance with the problem statement. Same thing, z is going to be 3. It says it right there in the problem statement. But then you can start writing the shell of your Gaussian quadrature integral. So we're doing n equals 50. The bounds on each of the integrals that you have to calculate are 0 to u. So we're going to do a equals 0.0, b equals u, and then Gaussian quadrature happens. And so you can just, at this point, copy down the shell of the Gaussian quadrature method that's in the book, which I'm going to do right now. It's going to be this guy, where instead of doing just one sum of the stuff, we actually have to do 2. So what I did there is I made a capital S, which is going to calculate this integral, but then we also have to have another one that's capital C, starting with 0 and going to C plus equals the same thing pretty much, except using the function C instead of S, right? So that's cool. After you do that integral, then you just return the formula, which is 1 over 8 times, and then in parentheses, and another set of parentheses, 2 times c plus 1 squared, and then it's plus 2 times s plus 1 squared, and then you divide the whole thing by 8, not 7. So yeah, that's pretty all straightforward. So that function is an array safe as per the usual, so we're going to, instead of making it run through the whole array, I'm going to create an x list, which is going to run from -5 to 5. So numpy length space -5, 5 with 1000 steps, and you just run for x in XLS. You just create a different list for the output, which is going to be the I list for the intensity list, and then you just append the list with values that you run through the function I sub x. That should be good, and then you should be ready to plot it against x and ILS. And just to be sure, this is based on this cell of code up here that came from, again, the online resources for Gaussian quadrature for the book. You do need to run and define those functions before you can actually do this one. So that should work now. And yeah, you get that nice intensity plot there. That is how it's supposed to look. You should find significant variation in the intensity of the diffracted sound. Yeah, you do. It's quite noticeable.